everyone. I am Chandrashekhar Choudhary, a PhD student working with Professor Towley at the University of Cincinnati. Today, I'll present our work on a battery-powered wireless sensor network for non-invasive monitoring of water usage events in premise plumbing systems. Some of you may have attended my talk yesterday for an accompanying paper of the same project and will find this background discussion familiar. So basically, peak water demand estimation is of utmost importance when designing the premise plumbing system for a new building, as it governs the size and cost of the entire water supply system. The traditional method for estimation, called the Hunter's curve, was developed in 1940 and has become outdated with broad adoption of water-efficient fixtures. This leads to significantly overestimated peak water demand and thus oversized water plumbing systems in both residential and commercial buildings. Oversized plumbing systems can trigger potential problems such as higher construction cost, wasted energy and water from inefficient water heating, as well as public health concerns on opportunistic pathogens like Legionella. A new method to provide greatly improved estimates of peak water demand has been recently developed and adopted in the National Uniform Plumbing Code in the US. However, it requires a critical piece of missing information on the probability or the p-value of fixture use during peak hours for all fixture types in a specific type of building. Estimation of the p-values for various fixture types requires collection of extensive field data on percentage of time when a fixture is in use from a large number of fixtures distributed in a target type of building. The data needed is essentially time-stamped binary on-off switching events, and flow rate information is not necessary. There are no solutions currently available with such a capability. To address this need, we developed a solution based on a wireless sensor network using a cluster of miniature wireless sensor modules deployed at each individual fixtures distributed in a building. The figure here shows the concept of the wireless sensor network system based on ZigBee protocol, which is a low power and low cost wireless communication standard suitable for mesh sensor network. The system consists of a cluster of sensor modules, several ZigBee routers, and a ZigBee gateway. Each sensor module in the network is battery powered for direct attachment to water pipe near a target fixture without the need of any cable or external power sources, and therefore can be easily distributed in the building at strategically selected sites for various types of plumbing fixtures. The ZigBee router will be deployed as necessary to help extend the coverage range of the network. The ZigBee gateway consists of a ZigBee coordinator and a Raspberry Pi computer unit. The coordinator interfaces with sensor modules and ZigBee routers and also provides time synchronization among all units to ensure proper timestamp recording of water flow events. The Raspberry Pi provides system control as well as data collection and management and interfaces with internet for data storage and backup in the cloud for remote interaction and with the end users using web applications. So the methods for water flow detection can be categorized into invasive and non-invasive types. Invasive types, while low cost and widely available, require changes of existing plumbing by cutting the water pipes and inserting sensors in line with pipes, making it challenging and costly to deploy, particularly at large-scale deployment sites. Commercial non-invasive flow meter products are typically based on ultrasonic sensors, which are sophisticated, expensive, and not amenable to large-scale distributed sensing. Very limited work has been done using other non-invasive methods like microphones for agricultural and smart home applications, and calorimetric sensors for air conditioning applications. The key advantages of non-invasive sensors is that they are easy to deploy and do not require changes to the existing plumbing, leading to significant cost savings. This makes the non-invasive sensors the more suitable choice in a large-scale distributed network. The center image here shows the hardware block diagram of our sensor module. It includes a flow sensor unit with multiple sensing modalities, a microcontroller or MCU with embedded ZigBee transceiver, as well as a rechargeable and replaceable battery along with power regulation circuit. The flow sensor unit combines two non-invasive sensing modalities to enable robust water flow detection with cross-checking and redundancy. Sensing modality 1 or SM1 is acoustic measurement using a microphone. Sensing modality 2 or SM2 is calorimetric thermal detection using a miniature heater and high-resolution temperature sensors. Details on SM2 were presented in an accompanying paper in yesterday's Emerging Sensor Applications session. SM1 is implemented using a miniature high-sensitivity MEMS microphone chip with a custom-built algorithm to detect water flow events in real time with resolution less than 0.25 seconds. The chosen microphone chip has a built-in feature to allow sound monitoring even in sleep mode with negligible power consumption and can send triggering signal to wake up the MCU and other components of the sensor module when the surrounding sound level exceeds a predefined threshold. This allows the sensor module to stay in sleep mode for most of the time and thus maximize its battery's lifetime. Only when the SM1 algorithm detects a water flow event, the SM2 function is turned on. As SM2 uses a thermal process, the power consumption is higher and response time is slower compared to SM1. However, it is less susceptible to environmental interference compared to SM1 and therefore can be used to cross-check the accuracy of SM1 detection. The estimated lifetime of the sensor module is more than 68 days when a high capacity battery of 10,000 milliamps is used. This image here shows the block diagram of the system software architecture. The sensor module software running on a Silicon Labs MCU includes program for data collection and data processing, algorithm for event detection in each sensing modality, as well as functions for Zigbee wireless communication, data management, and storage, and also power management of the module. The Zigbee gateway software includes the part running on the Zigbee coordinator for wireless communication with sensor modules in the network, as well as the part on the Raspberry Pi for functions like database operation, interfacing with the internet and cloud, and web server. The web server provides JavaScript-based application that can be accessed by remote end users through the internet to control and manage the sensor network, as well as download the data for processing and visualization. The implemented sensor module with package is shown in this slide. The 3D printed package includes a top case and a bottom case that are assembled together onto the water pipe using nuts and bolts for ease of deployment. In the top case, there are printed circuit boards PCB for the sensor module. There are also some features to assist with the integration of SM1 and SM2 sensors onto the water pipe. For SM1, a 3D printed flexible coupling ring is placed between the PCB and the water pipe to form an acoustic chamber surrounding the microphone port to minimize noise from environment and enhance sound capturing from the water pipe. For SM2, as described in yesterday's presentation, a 3D printed heater bridge allows the integration of miniature heater coil on the water pipe with minimized undesired heat conduction to the temperature sensors, which is critical to enable the calorimetric sensing function. The top case is also filled with sound and thermal insulation material to further reduce environmental interference, sound, and heat loss. The bottom case houses a lithium-ion battery of 10,000 milliamps capacity, and the overall size of the package sensor module is 12 by 6.4 by 8.1 centimeter cube. The sensor module circuit located in the top case is implemented on two custom-built PCBs. The main PCB includes a Silicon Lab MCU, a microphone, Zigbee antenna on the PCB with RF front end, heater driver, and power regulator circuit. The plug-in PCB for SM2 includes high-resolution miniature temperature sensors with large opening on the PCB to accommodate heater bridge as discussed in yesterday's talk. These components are placed on a separate plug-in PCB to prevent heat generated by main PCB components from affecting the SM2 operation. The SM1 algorithm developed using a DSP implementation for MCU allows fast real-time detection of water flow events from the sound recorded by the microphone. The algorithm filters the sound data to remove unnecessary noise and interferences and calculates a parameter named Signal Strength Indicator or SSI. Additional post-filtering of the SSI data is performed, and the result is compared to predefined thresholds to determine water flow events. Field tests were performed to verify the sensor module functionality in a cafeteria, restroom on an on-campus residence building at the University of Cincinnati. This figure plots the SM1 data of one of the captured water turn-on events, showing the effectiveness of the algorithm in removing background noise and in detecting water flow events. In one of the field tests, a total of 275 water flow on-off cycles were detected during a 24-hour period. SM2 test results were described in yesterday's talk and are not repeated here. Tests were performed on the overall wireless sensor network system, and the initial results are shown here. The test arrangement is illustrated in the left figure, showing the floor plan of the test site. Two sensor modules were mounted on a half-inch copper pipe nearby regular water faucets in two separate rooms. The ZigBee gateway was deployed in one of the rooms. The distance between the sensor modules and the ZigBee gateway were 3 meters and 18 meters, respectively, with multiple closed metal doors in between. Both sensing modalities in the sensor module were tested concurrently for water flow detection. The data was wirelessly transmitted from the sensor module to the ZigBee gateway and then downloaded through the internet using remote user interface running on a web browser. A subset of the recorded water flow events with timestamps are listed as examples in the table on the right. Both SM1 and SM2 sensing modalities were able to effectively detect water on-off events with a delay of up to 3 seconds observed between the timestamps generated by SM1 and SM2. This was as expected and considered acceptable. This test successfully verified the operation and functions of the wireless sensor network system for the intended application. This table summarizes the main performance parameters of the sensor module, as well as the sensor network. Most of them have been discussed in previous slides. The wireless performance of the sensor module was also tested. The ZigBee wireless link had a reliable transmissions for a range of greater than 36 meters without obstacles and greater than 26 meters with obstacles. In conclusion, we have developed a wireless sensor network with distributed battery-powered low-cost sensors modules for non-invasive detection and recording of water flow events inside water pipes. The solution has ease of implementation and ease of deployment. The function and operation of the system were successfully verified. The sensor network is ready for deployment at larger scale in field tests, which have been arranged for deployment at multiple sites around the university campus. Other future work includes exploration of other application scenarios. Our team members from the AIM lab at ECE Department of University of Cincinnati includes myself, my advisor and PI of the project, Professor Tauli, as well as other student members, including Gagan, Batra, and Tianshuo, Wang. The team also includes Dr. Omaghomi and Dr. Buchberger from Civil Engineering Department at University of Cincinnati. We would like to thank our sponsors, including NIST and Ohio Water Resources Center, as well as first field test site at Marion Spencer Hall at the University of Cincinnati campus. Thanks for your attention, and I'll be glad to take any questions.